Good morning, everyone. So we begin our last lecture on the topic of structured probabilistic graphical models in deep learning. In this last topic, we learned something to conclude our knowledge of how deep learning models learn probability distributions, specifically in the unsupervised learning way. So we have actually two parts in today's lecture. The first part is how the graphical models that represent probability distributions in deep learning differ from probability distributions learned by standard probabilistic graphical models. Probabilistic graphical models is a very big topic. Bayesian networks, Markov networks, studied in its own right uh, as a perhaps an area of probability in statistics, where one finds that the number of combinatorial possibilities is so large, it becomes computationally impossible to represent probability distributions using standard methods. So probabilistic graphical models come along to help you get rid of certain dependencies and represent it efficiently. So the question then is, how does that differ from how a deep learning model represents a probability distribution? So we'll begin with that, compare and contrast standard PGMs, or standard probabilistic graphical models, and deep learning models that learn distributions. And then the second topic is about a particular approach to representing probability distributions using deep learning, which is the restricted Boltzmann machine, RBM. We've seen that before. We'll once again take a look at it. I think it's very worthwhile to keep the RBM in mind. It may not be the latest, greatest method of representing probability distributions, but it is actually an excellent vehicle to understand how does a neural network or a deep learning model actually represent a probability distribution. How does it learn to represent a probability distribution? First of all, what does it mean to learn a probability distribution? That if I give you an example, an x is a multidimensional variable, a tensor, and the probability distribution should be able to tell me what is the probability assigned to that value. Is it a commonly occurring value? Is it a rare value? So on. Or we could use a probability distribution to generate samples from it that are reflective of the distribution. So this, we say, is an unsupervised learning problem. Understanding supervised learning from a machine learning point of view is pretty straightforward. We have an input and we have a label to be associated with an input. And if that label somehow differs from what is desired, we backpropagate, we change all the weights in the network. We keep going back and forth, forward pack, back prop, forward prop, back prop, until we learn all the weights. We're done. Supervised learning is easy to understand. So if I'm ask you the same question, how does unsupervised learning work, where you don't have labels? So how are you going to be able to generate some kind of an error value to update your weights? The answer to that lies in training the restricted Boltzmann machine. As an example, what we actually are going to be doing is any given setting of the RBM, any given setting of any generative model has a bunch of parameters. In a neural network, they're of course layered, so a bunch of weights. And together they represent a probability distribution along the lines of the Gibbs distribution. So there are visible units, hidden units, there are weights, and together we can define a Gibbs distribution representing the distribution of the particular network we have. The question then is, well, okay, how are you going to change the model based on the samples that you observe? And how are you going to generate an error signal when there is no supervision? So the answer lies in that we are going to be looking for a maximum likelihood estimation of the parameters. So is this the best you can do for this data samples that you have, or can you improve upon it? So it becomes an optimization problem. So how are we going to solve that is we take the samples from the data set and we run them through the Gibbs distribution that it represents. And we are going to see whether the parameters can be changed in the Gibbs distribution, because you need those W's. We'll see how those W's are used in the Gibbs distribution now. And can we increase that? How are we going to change that? So we come up with a formulation where we use the standard Gibbs formulation and we look at how to increase the value by again taking a derivative. So we end up having a derivative for the weights, and we take those derivative for the weights and add to the original set of weights. So gradient descent or gradient ascent is going to be an essential part of learning. Right? So it's a different kind of learning. So in the case of supervised learning, we have an error signal that's going to error signal, and we use a loss function, and that's how we train it. Here we use something like maximum likelihood. Of course, eventually some of these later models use other criteria, but we begin by thinking about maximum likelihood and how do we update the parameters. And that leads to a particular algorithm for RBM called as a CD or contrastive divergence. So that's where we're heading. I just wanted to lay out the roadmap. So we're going to begin by talking about how do the probability distributions represented by deep learning models differ from probability distributions represented by structured models, structured graphical models. And then we go on to how do we train a simple model in an unsupervised way in a deep network, and that is the training of it. So there are two subtopics again. All right, I'm going to share the slides now of today's lecture, and we're going to go through both parts within that same set of slides. Okay, so this set of slides, the last section of, I believe, chapter 16, which is about structured probabilistic models. This subsection is titled The Deep Learning Approach to Structured Probabilistic Models. This particular section is an important section. And after we talk about comparing the deep learning approach with the standard approach of probabilistic graphical models, we then look at the restricted Boltzmann machine and its training. So what is the special nature of probabilistic graphical models in deep learning? So we have two bullet points here. One is general PGMs, the other one is PGMs in deep learning. So let us recall what a general PGM is. PGM stands for probabilistic graphical model. The machine learning literature is full of PGMs. Every topic will have some diagram that looks like this. For instance, the first one here is HMM, or a hidden Markov model, where we have some kind of time dependency that the state changes from one state to the next state to the next state. And there is an output at each state. We observe that. So observed nodes in this diagram are shown shaded because we know the values. The task typically is to figure out what the values of the corresponding states here. These are called the hidden states here. There is a certain prior associated with each of these states, and there is a probability of obtaining a particular output. probability of transiting to a particular state and so on. That's an HMM. This was the original model used for speech recognition. And that is a standard graphical model, probabilistic graphical model. It's a directional model. Arrows represent causality. And in that sense, it is a Bayesian network. Here is a more complicated one, Bayesian network, where again, we have something like the last one, but it doesn't look like an HMM style here. There's some kind of dependencies here. And these are observed. And maybe these are the causes. And these are some values in between, all of which are unknown. So yeah, there are all kinds of probability distributions that people need to deal with. Like in a medical domain, we have observed symptoms and we need to figure out what the diseases are, which are unknown, but the symptoms are observed. And then we may go from some symptoms to some set of values, again, hidden values, maybe that certain category of disease or something, and then the specific disease, it could be like that. So anyway, those are general probabilistic graphical models. The reason we write those distributions in these kinds of ways is it provides savings in the number of parameters needed. If you just dealt with it as a full table probability distribution, it'll be just impossible to work with all the variables involved. And so probabilistic graphical models give you some kind of simplification that it's making certain assumptions. That's what a general PGM is. What about probabilistic graphical models in deep learning? In deep learning, they have a very specific structure, layers, and all that. So for instance, here we have observed variables called data space, and we have unobserved variables called latent space. The connectivity is almost complete from every latent model to all the observed models and so on in this particular case. And it actually has the structure of an RBM, or a restricted Boltzmann machine, which has got some observed values and hidden values. So what is the difference between these two? They got observed values, hidden values. So that's the issue in the next few slides, is what are the differences between general PGMs and PGMs in deep learning? And mention is made here that same computational tools are used. General PGMs is a much better established field. PGMs in deep learning, less well understood. And what are the computational tools that one works with is how do you learn the parameters? How do you, for example, HMM is very famous. Learning the parameters of an HMM, there are very classic algorithms for doing that. Some product algorithm and so on. So many different famous algorithms for HMMs and for any other Bayesian network. Some of those could be used here, and so that's for learning the parameters and then doing inference. When I give you a certain set of observation, for example, I give you a set of observation in an HMM, sound. I'm getting a sequence of sounds here on the microphone. And the goal is to say, well, what was just said? What were the words just said? I don't know, you tell me. So these are unknown values, and these are known values from known we need to do. That's the inference task. And so there are computational tools. How do you do that inference and so on? But there's a very different flavor in deep learning than these general models in PGM. So that's what's being discussed in these next few slides. So what are the differences? Differences in graphical model treatment. So we're saying all the world is about statistics, right? We're saying, give me a lot of data, I'll figure out, what is the world about. And that's the essence of machine learning and deep learning. And we have so many tools. One is simply work with tables, simply work with some approximate continuous distributions, or work with standard probabilistic graphical models, or we represent them using deep learning. So we look at it with a lens of 5 viewpoints. Depth, what kind of depth is there in these networks? It's how many layers and layers and layers, or what is the path length going from one node to another node? What is the maximum path length? We can define that as the depth. And we can also talk about proportion of observed to latent variables. So are all the nodes observed or unobserved, or a certain proportion are observed and certain proportion are latent? Right, that's a second category. Third one is latent semantics. What are these latent nodes? You don't even observe these things, and those are not even your final answers. And why do you need them, and what do they mean? And what about connectivity in inference algorithm? That is, what kind of dependencies we need to take into account. And then, of course, there is the issue of intractability in approximation. Invariably, PGM problems, working with them, the algorithms, the naive algorithms are intractable. Even though a PGM is a compaction of a real-world probability distribution by ignoring lots of dependencies that are irrelevant, still, as soon as you draw a graph and say these are the nodes and these are the connections, and won't you be able to give me an answer? If I give you some observations, can you tell me what is the value of the final output or something in between? The answer is, well, it's a problem which is actually Sharpie complete, which is you got to sum over all the variables, and summing over all the variables is an extremely expensive operation because every variable can take so many values. And not only is it an exponential problem, it is Sharpie complete in that you need to count all the possibilities, because you will need to do some normalization, which means counting all the possibilities. And that is even harder than NP complete. We call it a Sharpie complete. And so what are approximation algorithms to figure out? So these are all the issues. Wow, it sounds formidable, but this is what is needed. We need to work with the world of data, and we need to summarize it using a probabilistic model. So we're going to encounter all these issues. So we begin with depth in a probabilistic graphical model. So the depth of a model is the greatest depth between two nodes. Okay, so we can say that's the depth. Depth in a computational graph. In deep learning, we use computational graphs, which are different from the graphs of probabilistic graphical models. In probabilistic graphical models, the nodes are variables and the edges are interactions. Whereas in a computational graph, the nodes are operations. It's more like a computational flow. It's not exactly the same as variables, but we do have variables, and we have variables meet at an operation and so on. So we have a depth in a computational graph also represents a depth of operations. And we can use, and these computational graphs, generative models often have no latent variables or only one layer of latent variables. So we don't necessarily have latent variables all over the place in a deep learning. It might be one layer, two layers, three layers, so on, but not necessarily as large as it's possible in a general probabilistic graphical model. And we also say that probabilistic graphical models in deep learning are not deep PGMs. So they're kind of, 2 layers, 3 layers, 4 layers, and so on. Okay, so the depth was the first issue. The second is how many variables are observed or latent. And we're saying deep learning has more latent variables than observed variables. Okay, since it always uses distributed representations. Okay, even shallow models have a single large layer of latent variables. So we have many latent variables in deep learning. We see that first layer is observed, next layer is all unobserved. So that's quite a few latent variables. Whereas in a traditional probabilistic graphical model, they mostly contain variables that are observed. There is few latent variables. So we largely deal with, well, here are all the variables for whatever be the problem we're dealing with. And so we represent that by a graph, and we say those are all the variables. Where would the latent variables come from in a standard model? The standard model, and that I think is explained in the next slide. So what are these, where do latent variables come from? In deep learning, we architect it and we say we don't have any specific semantics ahead of time. What do those latent variables mean? And the training algorithm invents concepts to model the data. It is figuring out what does it mean at a higher level of abstraction and at another higher level of abstraction and so on. So we influence it, of course. And famously in a deep learning network, the latent variables are not easy to interpret. So that's the main complaint, saying it's a black box. How did you say it was a cat? Well, that's what the outputs at the last level before we applied softmax. And those are not necessarily human interpretable. And so the whole area of explainable AI is about how do you force it to make it interpretable. Whereas in traditional probabilistic graphical models, there are specific semantics in mind. When you design a PGM for some topic, such as learning the topic of a document, or it is about intelligence, or it is about disease-causing symptoms. For instance, we might have all these variables that we are observing, F, B, C, H, I. And maybe it's a supervised problem also, we know this value also, but there are a couple of variables in between here that may be latent variables. So what could those mean? Let's say intelligence. We might have, we saw this example earlier on chapter 13 or something, that we have got the scores of the student in several courses, maybe physics, astronomy, psychology, and so on. And we may have a certain theory that there are two types of intelligence. Mathematical intelligence is one of them. The other one maybe is spatial intelligence, right? Left brain, right brain type of thing. And we could say, well, we can't really measure that. We can't say, well, how good is your left brain or how good is your right brain? We can only observe your scores on the exams. But we have a hypothesis, those are possibilities. And we are saying the intelligence is dependent upon these two types of intelligence. And these two types of intelligence influence the kinds of courses you're taking. Mathematical intelligence influences your performance in mathematics and maybe physics or something, whereas spatial intelligence might influence your performance in art and geography and things like that. So we define something like that, and latent variables are there, but they're not numerous. What about connectivity in general graphs and deep learning? Deep learning graphical models have large groups of units connected to other large groups of units, so that interactions can be described by a single matrix. We are going from one level to the next level. So bang, a matrix multiplies all of the things coming in from the first level and gives you all the values at the next level. Whereas a traditional probabilistic graphical model have few connections, and choice of connections is individually designed. So one by one, we craft it. And the structure of the model is tightly linked to the choice of the inference algorithm. So if you're going to be inferring from inputs to outputs, so it's going to depend on the kind of connectivity. In traditional probabilistic graphical models, tractability of exact inference is an issue. And there are approximate algorithms for working with standard probabilistic graphical models. One algorithm is called loopy belief propagation. And so either exact or loopy, they work well with sparsely connected graphs. Whereas with deep learning probabilistic graphical models, graphs are not necessarily sparse. So how do you do inference with them? Well, there are approximate methods. These are famous probabilistic graphical model approximate inference methods. One is based on Monte Carlo methods or sampling. When you're dealing with Markov type networks, Gibbs sampling is used. How is it used? That's actually the topic of the next chapter, chapter 17. But sampling is used as a very quick way to get some expectations, right? Expectations are usually based on some over a set of samples, and you have a good set of samples. A small number of samples is enough to do inference. So sampling is a very popular approach to inferring with complicated diagrams involving variables and interactions. The alternative to a sampling-based inference is called variational inference, where we make some assumptions about the distribution, independences, and so on, so that we can invoke things like similarity of distributions, and then talk about what is the best possible tractable distribution to the current distribution we have. And that becomes optimization over all possible distributions. And that's where the word variational comes in, because we're talking about finding the best possible function. So it becomes variational calculus applied to inference. Ordinary calculus is about finding maxima and minima. Variational calculus is about finding the best possible function, right? So that's where the word variational comes in. So once we replace the given distribution by a tractable distribution, like it assumes some independence and so on, it's called mean field inference. Inference becomes straightforward with that. So that's also another approach to inference. So rather than simplifying the model until exact inference is possible, make model complex enough as long as we can compute a gradient. So with PGMs, we can use Gibbs sampling, we can use variational inference, or we can also structure it such that use gradients. That's the approach RBM uses. RBM doesn't use Gibbs sampling or variational inference, but it takes an approach of working with a tractable gradient. Bear with me, because till the end of the lecture, we're going to be actually looking at how does an RBM learn its parameters and how complicated it is. I have one slide summarizing all the equations that you need, and we'll try and motivate that. Okay, so now we begin with the specific example. Up to now, we worked with, we simply said broad things about graphical model representation, deep learning representation of probability distributions, right? Both are about modeling the world. Modeling the world is simply getting a good representation from which we can get samples, or we can infer any probability. So now we go to a specific example, restricted Boltzmann machine. Apparently there is an old word for RBM referred to as harmonium. I don't know, it looks like a harmonium maybe. We in India may be familiar with harmoniums. It's not a very common musical instrument, but maybe that's what all the inside of a harmonium looks like, right? There are keys and there are notes, I suppose. All right. So RBMs are a quintessential example of how graphical models are used for deep learning. RBM itself is not a deep model. All we are showing is one layer of observed variables and one layer of hidden variables. There is no output here. It is just that. What it is doing is learning a distribution of the data, using the latent space as the way to capture interactions between variables, rather than having any kind of direct connectivity between these variables. That's why we call it a restricted Boltzmann machine. A Boltzmann machine is any kind of general graph. Restricted Boltzmann machine says, oh, you can only have these connections. All right, and RBMs can be used to build many deeper models. We can stack them together called deep belief networks and so on. But let's just understand RBMs. This slide is simply giving an explanation of a general Boltzmann machine and a restricted Boltzmann machine. In a general Boltzmann machine, we have variables H1, H2, H3 here, and then we have V1, V2, V3 here. Whereas in an RBM, there's no connectivity between H1, H2, and H3, and there's only connection with the VRs. So the RBM characteristics are that the units are organized into large groups called layers, and connectivity is described by a matrix. Connectivity is relatively dense, and it is possible to do Gibbs sampling with an RBM. And it learns latent variables whose semantics is not defined by the designer. So we learn some latent variables. Okay, an RBM drawn as a Markov network. The model is, okay, we got to follow these equations carefully, all right? You got to be with me because that gets used in deriving the training method. These are not as complicated as giving all the equations of backprop for a supervised learning. We're talking about figuring out how does an unsupervised learning model learn. So we need all these. Okay, let's go with this one. We have, this is the network, V's and H's here. We have learned that given any Markov network, I can draw a unnormalized distribution of the Markov network. P tilde of VH, that's the unnormalized distribution. And that can be written as exponential minus EVH. So we are now using the energy formulation. When we studied Markov networks, we began with factors, and then we said, with a simple sleight of hand, we can replace the factors by taking the negative logarithms of the factor values. We can have an energy representation. So this energy representation, EVH, what is this EVH? Is V transpose V, C transpose H, V transpose WH. All this is saying is there are a bunch of parameters W between the two, between the V's and the H's. And there are some biases B associated with V and the biases C associated with H. So we have a set of parameters B, C, and W. The important ones are the W's here. And we can also talk about the joint distribution that this represents as X is equal to V comma H. So X is all the variables. VH are the two subsets. So we can write this as the standard Gibbs distribution. P of X is equal to 1 over Z P tilde of X, or P hat of X. What is Z is integral of P tilde of X, P of X dx. So we have here stated what is this P tilde? P tilde is this, where X is stated as V comma H, is exponential. So we know what Z is, and we know what, in this case, P tilde, this should have been P tilde, not P hat here, P tilde. And P tilde of X is the same as what we just talked about here. So this set of equations exactly specifies the probability distribution represented by a restricted Boltzmann machine, where we have W's, B's, and C's coming into play. And so that's the complete definition of a probability distribution. And we're going to work with that. And of course, it's a restricted Boltzmann machine. We know what that is. In a neural network, we have things like X's and H's and Y's, typically used in supervised learning, or X's go to H's to Y's. And we can break them apart as H1, H2, or we can include them here as H as a vector. X is a vector instead of X1, X2, it's all one here. So I'm just saying same thing can be done here. V1, V2, V3 can be written as V. H1, H2, H3 can all be written as H. So that's what's being done in this diagram. We go from X's to H's. There's a W here. which is playing the role of multiplying all of these. It's got a whole bunch of Wij's as part of that W. Similarly, H to Y will have another matrix. So we're saying the H matrix or H vector is given by G of W transpose X plus C. And the G function could be a ReLU, max of 0, Z is the ReLU function. And of course, we need a whole vector out of it. And then Y, it could be a scalar value, H transpose W plus B. This is the form we use in the next slide. We're going to talk about the RBM in this way, X, H, Y. When we denote them as vectors now, and then we have a capital W as a matrix, and then we have a vector W here at this level, and so on. So the network view of RBM is this, that we have a V vector, visible layer, H vector, the hidden layer, and for an RBM, we are treating this as binary units, and this formulation assumes V and H are binary for some simplification. So we have a binary image as input, and it's learning. So like let's say an image is not a color image, binary image, and the hidden layer also are binary value, and then there are connections between these, and there is somehow the ReLU coming in between. So EVH, so if you have learned all these W's, and for any given V, and we have certain values of H based on the W, then the EVH is given by B and C are also parameters. Let's say we are setting for all of these. So it's BV times CH minus V transpose WH. And that relationship is expanded out in terms of all the values in these matrices. So we said PVH is exponential minus EVH divided by Z. So this is saying that the network actually is able to define a probability distribution between the V and H. So for this set of inputs and this set of H values, we have a joint distribution of P, V, and H. If we wanted only the probability associated with V, we need to just marginalize out the H, and that will give us a marginal distribution. So one important simplification that comes about in an RBM is that it has this nice property that probability of H given V. So this is a conditional distribution. P of this H vector given this V vector is nothing but product of HI given V. So these are independent. And then V given H, the other way around, is equal to probability VI given H. Well, that comes about because of the nature of the assumption of the restrictions. And if such is the case, the individual conditionals are simple to compute. For a binary restricted Boltzmann machine with VH belongs to 0, 1, we obtain P of HI equal to 1 given V is equal to sigmoid. We transpose a vector from the W matrix plus PI. Similarly, HI equal to 0. So we get some simple versions involving sigmoids over here. And one more observation we're going to make is that it is possible to apply Gibbs sampling to this network. And we saw what Gibbs sampling is. I just reproduced it in this slide. If you remember, Gibbs sampling with M variables, initialize the first sample of all the variables, and then you sample, set all of them to the initial sample values, and you calculate a distribution over Z1 given all of that, and you take a sample from that conditional distribution. And we just said in the previous slide, the conditional distributions are straightforward. If that's the case, then you can sample from it. Give me a sample for Z1, given all the other values. Similarly, fix the value of Z1 and then give me the value of Z2, and then fix all the others, give me Z3 and so on. So, and then we keep on doing this, and we are able to get some steady state where we get Gibbs samples from this distribution. So, keep in mind, I'm going to use this idea shortly for the learning part also. So right now, all we have talked about is I have a RBM, and it is possible for me to generate samples from the RBM if you know all the parameters. If you know all the W's, B's, and C's, then I can start giving you samples. And people did that. What they did, it was, can we train an RBM on MNIST handwritten digit data, 0 through 9, all binary images of the handwritten digits. This is people have written pen to paper. They've been scanned, and we are generating. We are using a particular RBM now to train on them, and this says for a. These are samples actually. Each column is a separate Gibbs process. Each column, top to bottom. Each row represents the output of another 1,000 steps of the Gibbs sampling. All right, each row here. Successive samples are highly correlated. So we are showing that we're generating these values going from one to the next, to the next, to the next, to the next, to the next. And then of course we generate new ones. So if you remember in Gibbs sample, it's just changing one variable at a time. So it's probably going to give you something quite similar to the previous one. And then at some point, it is going to make a jump. And so we are generating these samples, and we are actually doing this again and again. The different separate Gibbs process. Again, we start at some point, get this one. Start at some point, get this one, and so on. Corresponding weight vectors. So these are the W's being illustrated at each point in the form of an image, what it is learning. Anyway, maybe that's not as intuitive. Main point here is that an RBM could be trained on MNIST digits, and you could start generating samples out of it. Actually, the samples generated out of an RBM are better than samples generated out of another model called the linear factor model, example PCA. You could use principal components analysis also to generate samples called sparse coding. And it turned out the RBM gives you sharper images than sparse coding. It's an interesting observation, where the model uses this formulation where you've got a directed graphical model, and you have X is equal to WH plus P plus noise. So anyway, it's an interesting experiment. So now what we're going to do is, okay, so let's summarize. I hope it's not getting too complicated. We just have a restricted Boltzmann machine, 2 layers, and we have also figured out it's possible to sample from it if you give me all the parameters. Straightforward to do that. Now we're going to head into how are we going to get those parameters? How are we going to learn those parameters? Just like we know how to learn parameters of supervised learning, how do we do parameters of unsupervised learning? So now we have, again, energy function, EVH. Keep in mind that the network here represents a probability distribution. It's a very different kind of thing than in supervised learning. Supervised learning, we don't say the network is about a distribution. Right? We just care about the input-output relationship and the matrices that multiply them with, and then the activation function and so on. We don't pay attention. Together, what does the network know? And now we are focusing on what does the network know? We're saying the network has an associated energy function, and an energy function is inversely related to the probability. What's the probability it assigns to PVH, or the entire set of values is defined by the energy function. And say, since the energy function is a linear function of its parameters, it's easy to take derivatives. What are we going to do is we're going to take the derivative of this energy function. What? Why do you want a derivative of the energy function? Because we're going to be using it in the learning process. Derivatives come around. Calculus comes around whenever you want to do learning. we were doing derivatives of the loss function for supervised. Now we are doing the derivative of the probability value, and you can imagine how that's going to be used, because we're going to be saying, let us maximize that or minimize that. What kind of parameters would make that EVH high or low? That's why we want the derivatives. And there are two things we have observed. We have observed Gibbs sampling. There is an efficient Gibbs sampling possible because the conditionals are easy to compute. And there is an efficient way of computing the derivatives. If you want the derivative of EVH with respect to Wij, it is nothing but Vi times Hi. Oh, wow. Derivative is simply multiply the current values of Vi and Hi, the weights associated. So training undirected models. Training undirected models is accomplished by computing the derivatives and applying it to samples from the model. So we are going to be getting samples from the model. Oh, okay. So we're going to be getting samples from the model. We have got real samples and we got samples from the model. Training induces a representation H of data V. And we can use expected value of H with respect to the conditional distribution of H as a set of features to describe V. Okay, it's not very clear at this point. On the next slide, it makes it clear. RBM demonstrates the typical deep learning approach to graphical models is representation learning accomplished via layer-wise latent variables combined with efficient interaction between layers parameterized by matrices. Okay, it's all efficient, but we want the concept. So these slides try and get you the concept. So you got to kind of concentrate on what's going on here. We just said, here is the RBM, right? We got all these visible units, we got all these hidden units, we have the W connections, we have things like bias, AIs here, BJs here. Slightly using different notation than the previous slides. Call these AIs associated with V and BIs associated with H. So the joint configuration VH, visible and hidden units, has an energy described in a famous paper by Hopfield in 1982. I guess that's nearly 40 years ago. He said, well, this kind of a network has an energy function and an associated probability distribution. The energy function is summation AI BI, I over all the visible, summation BJ HA, J over all the hidden, and VI HA WIJ. So we got VI HA interacting here with the WIJ, that's the W connections over here. So a network assigns a probability to every pair of hidden and visible vectors. And it says for any V and H, PVH is this. So it's saying, if I give you any visible unit and any hidden unit set of values, I can give you a probability associated with it. And that probability is, as you can see, it's e to the power of minus EVH. There is a kind of a inverse relationship. As EVH becomes large, PVH becomes small. As EVH becomes small, PVH becomes large. That goes into the intuition in physics. Because physics guys were talking about energy and probability, and they were talking about how high energy configurations of atoms in a gas in a jar, high energy has low probability and low energy has a high probability. This is all statistical physics. We're saying the same thing here. We're saying there is some energy being modeled here by the network, and the probability distribution has an inverse relationship with it. And it also got this Z called partition function. That's a physics guy's terminology. And that is saying it's sum over all the possible values of V and H. That's what's going to make this intractable. All possible values of V and H. That's an enormous number of possibilities, which is what makes it an exponential computation complexity. Anyway, the probability that network assigns to a visible vector V. Supposing we say, well, what is the probability associated with this image? I've got this one MNIST image. What is the probability of this one? Okay, no problem. We will just sum over this joint probability. The joint probability is given by EV minus H. Sum out the H variable. This is this usual trick we use when we are given a joint distribution and we want to get a marginal out of it, is to sum out all the values of H. And that gives you. So keep in mind that this restricted Boltzmann machine, it's not simple Boltzmann machine, it's a restricted Boltzmann machine, represents energy, represents a probability distribution, and can also give us the marginal probability of just the visible unit. So all of this is possible in such a simple design, which encodes all of this. So if we want to change the probability of V, we just saw what is the probability of V. Probability network assigns to training data can be raised by adjusting weights and biases. Why do you want to raise the probabilities? That's the idea of maximum likelihood. What are the sets of weights and biases that are going to give it the highest probability? And lower the energy of that image and raise the energy of other images. So that image, raise the energy. Okay. So especially those that have low energies and make a high contribution to the partition function. So partition function plays a role. And so now let us start by, we're going to use, basically we're just saying, we're going to figure out the weights in the learning phase by maximum likelihood approach, which says, well, the joint probability of a set of samples PV1 through VM, right? Let's say we had M samples, and we want to have the parameters such that this is going to be maximized, right? That's a standard method of maximum likelihood. So we have product of the individual. We know what PFV is. We saw it in the previous slide. We're multiplying it over all the M values. That's the likelihood function. Let us take the logarithm of this equation. So it says logarithm of this is the log likelihood. This is the likelihood of this is the joint probability of all these independent. The multiplication comes about because we're assuming all the samples are independent. And so we're taking the log of it. That log converts this product into summation, logarithm of this. And we know the expression for PV. The previous slide told us that is all in terms of the energy function and the partition function. And then we do some algebra and say there are two terms here. There is one term like this, summation over M. This is sum over H, and then this, EV minus H. That EV minus EVH occurs here also, and we're summing over V and H over here. That's the partition function part of it. All right. How did we get this? Is the Z is there, you see. The Z is 1 over Z. When you take the logarithm of 1 over Z, it becomes a negative term here. That Z is all what's causing this whole thing here. And this is the first part of it. So that's all it is. So we have applied the definition of the Gibbs distribution and partition function to come up with an expression for the log likelihood. So we're saying we're going to maximize the log likelihood. We have gotten hold of what is the equivalent of the loss function. What are we going to optimize? And this says take the derivative of this expression. This is the partial derivative with respect to Wij of PV. We're looking at one term over here. Is equal to expected value. Okay, we're looking at all of these, the summation over all the samples. So this is, and we said the derivative was a form Wij. Previous slide said that the derivative has that simple form. So Wij is occurring here. And when we sum over samples, we can say, well, that's the expectation. And this is saying the summation is over the data samples. All right. And this one is saying it is the summation over the model. So the second part is the summation over the model, and the first part is the summation over the data samples. So we have the model is EVH, right? This is the particular set of samples here, M, and this is over VH, EVH, the model itself. So summation over the samples from the model, and this is summation over the samples from the data set. So we need two types of data here. One is the training data, and then we need samples from the model we have. It's a very peculiar phenomenon here. So we have two types of data here to figure out this likelihood. So the learning rule for stochastic steepest ascent is the derivative delta Wij is equal to some learning rate epsilon. E data, E model, where epsilon is the learning rate. So this is saying the error for the gradient step. So we got a certain W, we need to change this W. So it says, well, you give me E data, or expected value with respect to the data, or VIHA, expected value of VIHA with respect to the model. So you see, this is what leads to a very beautiful algorithm, contrastive divergence, which is saying there is all this data you are trying to fit with your model. And you have a certain model already conceived, and you can generate samples from it on your own using Gibbs sampling. So I got this real data and I got the model data. We're trying to resolve the two, and we're computing the expected value over this data set and over this data set. How different are they? That is what is going to drive your change in the WJ. So it's very different from supervised learning, where we had an external signal telling us what to change. This is saying the model has some idea and the data has some idea. And Jeffrey Hinton gave a nice analogy to what's going on here. He said, think of it, we always think about how does all this correspond to the human brain. And we can think of what's going on in this unsupervised learning problem as the wake sleep method, the human brain. So let's say, we go to sleep, right? We have a model of the world in our sleep. May not be very perfect, but we are playing it out in our dream. So we can generate samples. Let's say we're going to be able to generate samples from our dream. So here is a set of samples. The dream is the model that we have in our head is the current model, and we can generate samples. And then we wake up and says, well, this is what the real world is like. Well, that is the true world samples. So the model in our brain may not be exactly the same as the real world. So the real world gives us some data. Now we're saying, okay, we got to change our model in our brain to fit the real world better. The current model may not have been very good. Right? We're imagining something. Let's say we are thinking of imagining going to, let's say, some place we've never been to. Maybe some place in let's say a big city we've not been to, Las Vegas. Let's say we've never been to Las Vegas, but we have some idea of what Las Vegas is, but it's a rough idea. And then we actually go to Las Vegas and say, this is what it's really like. Oh wow, I'm going to change the current model in my brain. All right. And so this is based on samples we're acquiring. This is the beauty of unsupervised learning, which is much more interesting than supervised learning, where we're saying, is this a cat? All right, it's not giving me a cat, go change the values. That is so mundane compared to unsupervised, which is an entire distribution captured. So then comes a little bit of mechanics here. So we need to get samples from the data, we need to get samples from the model, and we need to get unbiased samples from the data of VIHA. This is saying we got to estimate the value of VIHA. So we generate samples. Given a random training image, the binary state HA of each hidden unit is set to 1 with probability VHA. So we can choose the values of HA from that. And then given a random training image, the binary state for a visible unit 1 is set with probability this. So we can generate a value of or samples from it, we're going to do the expected value of that. That is, we average all of that. Similarly, getting unbiased samples from e-model. So first one is getting samples from the data set. The second one is getting unbiased samples from the model. Can be done by starting at a random state of visiting unit, performing Gibbs sampling. Basically, we're saying use Gibbs sampling. This is like, how do you generate samples from your model? Well, use Gibbs sampling. And then, of course, you need to get good samples from the data also. We want a specific one, VIHA. So that's telling you that there's a certain way you can do it. This is a grand slide I prepared, which summarizes all of RBM training, all the equations we need. So we need to kind of have this full picture to have an idea of what's going on in training in RBM, which is the simplest of the models of unsupervised learning models. So we have here a Gibbs distribution. Theta is all the set of parameters that go into it, right? Z is also a function of these parameters, theta. So what is theta? Theta is WAB. These are all the parameters of this RBM. For an RBM, X is equal to V comma H. So what is X? X is V and H. That's in this diagram. V and H are given. So we have the joint distribution represented like that. So we have to determine parameters theta that maximize the log likelihood. And then the log likelihood L is written in this way. It's got the first term, which is from the samples. And this is the second term, which has got the Z function or the partition function. And we are making explicit use of the energy formulation and the relationship to probability formulation. From that, we learn that the derivative of Wij is given by, of EVH, of this energy function is given by VIHJ. And that's what we're going to resolve here together. So we have GM for stochastic gradient ascent, the derivative GM is given by the derivative. These are two parts to it. So that's how we get G for the mth sample, and we over all the samples, we compute G and then we update theta. That is a standard gradient descent. We take all the parameters, update them based on all the samples G obtained by taking the difference. So this says computing this derivative term has two parts to it. There's a positive phase and there is a negative phase. This one is referred to as a negative phase. So one is trying to increase something, the other one is trying to decrease something. So because both are positive terms that are contributing to it. Derivative of the positive phase, derivative of the negative phase. So this is saying these are the expressions for that. So that's what's going. So these are the equations, all of which have to go in to train a restricted Boltzmann machine to learn the distribution of data. Now, why is this an important building block for those of you who are trying to study machine learning or deep learning? This is the sense of how to learn a probability distribution by using a deep learning network. And the name of the game in all deep learning is to learn probability distributions of the training data. And of course, you can say, well, I don't care about RBMs. I want the latest and greatest method called GAN or VAE and so on. Well, those are all just variants. And all of them are about learning probability distributions. And they have cleverer tricks to do it. But remember, even when you go to something like GANs, you remember in GAN, we talked about it briefly on some of you may be very familiar with GANs, where we talk about the training data and we are trying to fool a discriminator into whether this example came from the training data or it came from the model, right? We keep on training it like that. So you see, we are comparing training data with model data. And we are saying, where does all this come from? Is this, we have shown that the derivative that you compute to modify your parameters have two parts, one coming from the model and one coming from the data. And we have mathematically shown where does all this come from? And it comes from the Gibbs formulation, it comes from the energy formulation, it comes from the nature of the derivatives. So this is an absolutely beautiful topic to explain it, all right? And this is all stated by Geoffrey Hinton in his famous algorithm called contrastive divergence, and a method to overcome exponential complexity in dealing with the partition function. It is defined for an RBM only. So you can say, well, you know, what good is that? It's just RBM is what, 2 layers, input layer, hidden layer. Of course, you could stack them and stack them. You could get a much more complex one called deep belief network. Of course, we have gone away from greedy supervised learning to more complex models. But anyway, that's just adding some level of complexity to the model. But so I would recommend to you, if you want to go away from machine learning saying, do you know how machine learning works for supervised learning? Okay, that's easy. Cats and dogs and error signal. Then I ask you the question, do you know how unsupervised learning works? Well, you'll have to think of this. It's very useful to think of it. Maximum likelihood formulation of figuring out the parameters, and that involves dealing with real data, dealing with model data. That's how you update it, okay? So that is how you can remember, how does unsupervised learning work? Okay, so that is it for today. Happy to take any questions that you might have based on today's lecture. All right, let me know. Okay, I'm going to stop the recording.